Hello and welcome back to another video lesson of Math 1106, Math for Business Pre-Calculus. My name is John Adamski. You may have noticed that my voice is a little different today. I'm a little bit sick right now. I'm feeling okay. I think I'm well enough. I can get through today's lesson. So what is it? This is week 6. We're going to talk about functions. We've wrapped up our discussion of algebraic topics. We ended that last week. Up until now, we've been discussing algebraic expressions involving exponents, denominators, how to factor algebraic expressions, and how to put all of that to use solving equations. That was last week's lesson, solving equations. But now we're going to move on. All of that stuff is going to be used, but we're going to begin the pre-calculus unit where we are going to study functions. And when you do take calculus, you will be studying functions. Calculus is a particular way of studying functions. So we have to be very clear what functions are. So we'll begin with a definition of what functions are. Going hand in hand with that is the domain of a function. We'll define that. And that will really be our focus for the rest of today's lesson. And we'll learn how to use interval notation to describe the domain of a function. So that's the plan. Let's get to it. All right, so what is a function? Here's the definition. A function is a rule that assigns exactly one output to every input. Okay, it has everything to do with inputs and outputs. Input is what goes into a function. A function follows a rule or a procedure or a program or an algorithm to, from that input, produce some output. That's it. That's what a function does. Here's an example. I'm giving you some inputs and telling you what the corresponding outputs are. What rule is this function following? What is the function? Well, this one's a little bit cute, and maybe you can come up with a different way of getting these same outputs from these inputs. But what I had in mind is, if I get on a northbound 1 train at 14th Street, and I ride it for 1, 2, 3, I ride it for this many stops, this is where I'll find myself. If you ride it for 1 stop, you'll be at 18th Street. For 2 stops, you'll be at 23rd Street. For 4 stops, you'll be at 34th Street, Penn Station. 5 stops, you'll be at 42nd Street, Times Square, etc. Okay, that's a very cute example. It's not really one that we're going to study much in this class for many reasons. One, if you were to enter 23 as input, if you ride the 1 train for 23 stops, you're going to find yourself at Dyckman Street. In Inwood. Well, that's not a number, and so this is where the math must stop. There are other problems associated with this too. For example, if you input the number 1/2 into this function, and you try to follow the rule of riding the 1 train for 1/2 stop north of 14th Street, that doesn't make any sense. I don't know what this function should output. That means that 1/2 is not in the domain. That's not acceptable input for this function. The rule that I was following, riding the 1 train for this many stops north of 14th Street, doesn't make any sense when you plug a number like 0.5 into the function. That would cause this program to crash. Okay, not only do I not know what output should come out, but there's no way of knowing. Okay, so that's not acceptable input, and so that is not in the domain. The domain of a function is the set of all allowable inputs. You're not allowed to input 1/2 into this function. Can't accept it as input. Okay, here's a more practical function, one that's closer to what we're actually going to be studying in this class and in calculus. These are the inputs, these are the outputs. I'm trying to figure out the rule that goes from here and produces these numbers. Okay, if 2 goes in, 1 comes out. If 3 goes in, 4 comes out. If 4 goes in, 9 comes out. You might recognize that the numbers on the right-hand side are all perfect squares. And it just so happens that 1 squared is 1, 2 squared is 4, 3 squared is 9. They're kind of off a little bit. The rule here is to take the number x and subtract 1 from it and then square it. That's a rule that will give you these outputs. Okay. Here's another example, and this is more in line with what we'll be doing in this class. I'm just telling you the function. The function is 2x squared plus 3. What does that mean? Well, the function is the action. The function is the rule that's being described here. Up until now, we've been so focused on, the algebra of this. Can you factor it? Can you solve an equation? I'm not trying to do any of those things right now. I'm just trying to focus on what this function does. And if you tell me what x is, this will produce some output based on the input. So I'm just setting myself up for what's about to come. I want to plug some numbers into f. And if you look at what I just did, I got rid of all the x's, and in their place, I put open parentheses. This is a good template now for what's coming up. I want to plug things into my function. I want to know what is f of 0. Well, f of 0, see I'm replacing x with a 0. I want to do the same thing over here. I want to replace that x with a 0. There's only one x on the right-hand side, so I'm done. I just have to figure out what number this is, and I have to make sure that I follow the order of operations. If I do, I'm going to get the right answer. 0 squared is 0. 0 times 2 is 0. Plus 3 is 3. So f of 0 is 3. When the input is 0, the output is 3. When the input is 5, what is the output? What is f of 5? Well, I'm just going to do the same sort of thing. If 5 goes in, this is what comes out. That's 5 squared, 25, times 2, 50, plus 3, 53. 53 comes out. And if negative 5 goes in, well, this is an example of why those parentheses are important. Negative 5, the number gets squared, and negative 5 times negative 5 is 25. Times 2 plus 3 is 53 once more. Okay? Now, what is the domain of f? What numbers are you allowed to plug into this function? Are there any numbers that you couldn't work with? Well, I think fractions are okay. You can square fractions. You just square the tops and bottoms. You can multiply any number you want by 2. You can add 3 to any number. Actually, I don't think that there are any numbers that you cannot input into this function. I think you can input all real numbers. All real numbers. And another way to write all real numbers is with this symbol, which is a capital R with 2 vertical lines on the left. That's a symbol that throughout all of mathematics always means the set of real numbers, all of the real numbers. What do I mean? Well, you're familiar with a number line. What numbers are all the real numbers? All of them. So sometimes we do visualize the domain by graphing it on a number line. And if all real numbers are in the domain, then all real numbers get lit up. And this is the domain of that function. OK, let's look at another example and use it as an opportunity to further discuss the domain of a function. If I let g of x equal the square root of x, what's g of 16? Well, this is telling me what the rule is. Take the square root of the input. The input is x. The output is the square root of x. If the input is 16, the output is the square root of 16. That's 4. OK? And so in particular, since plugging 16 into this function didn't lead to any errors, didn't lead to any crashing of the program, 16 was a perfectly fine number to work with. It's allowable input. It was in the domain. What about 2? G of 2 would be the square root of 2. That's fine. That's about 1.4142. Keeps going. It's not a whole number. It's not even a fraction. But it's fine. This program is going to run. No problem. 2 is in the domain. What about 0? G of 0, following the rule, would be the square root of 0. The square root of 0 is 0. Some students think that the square root of 0 is undefined or something like that. But no, the square root of 0 is 0 because 0 squared is 0. So 0 is also in the domain. What about g of negative 4? Well, g of negative 4 would be the square root of negative 4. And now we are hitting a problem. This program is now going to crash. You would get, if you entered this into a calculator, your screen would probably say error. Okay? You can't take the square root of negative numbers. There's no number that when I square it gives me a negative number, unless you allow imaginary numbers, and we don't in this course or in any of the calc courses. So in this case, -4 is not allowed to be the input. It is not in the domain. -4 is not in the domain. Okay, and so it's pretty easy to go ahead and check if a particular number is in the domain or not. You just try plugging it in and seeing if you hit any problems. And if you don't, then the number is in the domain. And if you do hit a problem, then the number is not in the domain. So instead of just going one number at a time and checking, is it in the domain or is it not, can you answer just at once, what is the domain of G? What numbers can you plug into this function G? Out of all the real numbers, which numbers can you plug in? Well, we've kind of already said it. The numbers that you cannot plug in, the numbers that are not in the domain, are the negative numbers. Those are the numbers that are not in the domain. So what numbers are in the domain? Well, it would be the non-negative numbers. Being really nitpicky here, I'm not saying the positive numbers because 0 is not positive, but it is in the domain. So it's all of the numbers except the negative numbers. It's the non-negative numbers. That's the domain. That's how I would say it in words. If I wanted to describe it in inequalities, the convention is to use x to represent input, and I'm saying that the input needs to be greater than or equal to 0. And I could, of course, draw that on a number line and visualize what are the numbers that are greater than or equal to 0. It would be these numbers. There's another way, a fourth way, in addition to words, inequalities, and graphs, there's a fourth way called interval notation, a way of describing intervals like this. And now we'll talk about that. All right, I want to leave functions behind for just a second, functions and their domains. We'll get right back to that. But what we've seen so far is that when you ask what's the domain of a function, often the answer is all numbers bigger than this number or all numbers smaller than that number. And what we're describing there is an interval. And there's a notation for how to describe intervals in mathematics. So before we get to how to answer questions about domains and more of that, let's just focus on how to present our answers using this notation. It's called interval notation. So let's begin with an inequality that looks like this. Suppose you arrive at somehow this inequality where you know that x is both bigger than or equal to a and less than or equal to b. Another way to describe that is visually. If this is the case, then x could be a, x could equal a, x could also equal b, or x could be some number, any number in between a and b. So it could be anywhere in the middle. This is a visualization of that set of numbers, that interval of numbers. And in interval notation, the way that we would write this is we would say, okay, well, it's all the numbers from a to b. You'll notice that I have the smaller number on the left and the larger number on the right. Okay? If I'm thinking of all the numbers from 2 to 3, I have to write 2, 3. I can't write 3, 2. It's all the numbers from 3 to 2, but we always put the smaller number on the left and the larger number on the right, with a comma in the middle. Yeah, now I'm going to put some symbols on either end. I'm going to put hard brackets. I'm going to put brackets here and bracket there. A bracket indicates that the endpoint is included. Okay, so whether I put this symbol here or this symbol here, those are both bracket symbols. That's to indicate that the endpoint is included. Okay, cool. Well, what about this inequality? It's very similar to this one. It still says that x is between a and b, but now x is not allowed to equal a. X has to be strictly bigger than a. And x is not allowed to equal b. It has to be strictly less than b. So the picture looks a little bit different. It's all the numbers in the middle, but since I'm not including a and I'm not including b, I emphasize that by putting some open circles here. Now truly, the only difference between this set and this set is that I'm removing just 2 single points, and points don't have length. So really, visually, there shouldn't really be any visual difference between these. But this is an important distinction that we want to emphasize, so we're calling attention to the fact that A has been removed and B has been removed. The numbers in the middle are still there. Okay? The way that I notate this is the left endpoint is still A, the right endpoint is still B, but since neither endpoint is included, now we put parentheses here. Okay? So these symbols, the parenthesis symbols, are used to indicate that the endpoint is not included. Okay? So that can be a little bit of a big deal. At least in mathematics, we care so much about the endpoints that we're introducing different notation for when they're included and not, because this can be a big deal. For example, if I was looking at the numbers from 0 to 1, it should be fairly obvious that among these numbers, 0 is the smallest and 1 is the biggest in this set. I'm using interval notation here. If I were to look at the set 0, 1 down here, well, again, on a number line, that would look like this. You would have 0 over here and 1 over here. And I can ask you, what's the smallest number in this set? Well, it's an interesting question, because certainly, the number 0.1 is in this set. It is to the right of 0. But so is the number 0.01. That's also in here. And so is the number 0.001. That's also in here. We're getting really close to that left endpoint, but the left endpoint isn't included, so you'll never be able to touch that left endpoint. All you can do is get a little bit closer, a little bit closer, a little bit closer. There's nothing stopping me from doing this forever. No matter what positive number you name, there's always a positive number that's smaller than that. So there is no smallest number in this set. And similarly, there's no largest number. 0.9 is in here, but so is 0.99, and so is 0.999. All of those numbers are between 0 and 1. Again, this set would have a largest number, 1, but this set does not have a largest number. And for that reason, these are quite different sets. And so we're emphasizing that by giving different notation to the endpoints. Now that I have both brackets and parentheses, I can start to mix and match. For example, here I have an inequality that says x is greater than or equal to a. So it's equal to a or bigger, and it's less than b. So it's not equal to b, it's just less than b. Visually, graphically, this is what that looks like. And in interval notation, I would say, well, those are all the numbers from a to b. A is included in that interval. B is not included in that interval. So this set has a smallest number in it, A, but it doesn't have a largest number. Whatever number you point to, you can always move a little bit to the right and get a larger number in that interval. And in the bottom here, I have x is strictly bigger than a, so x cannot equal a. X has to be equal to b or less than b, so I think the interval would look something like that. This interval does not have a left endpoint, but it does have its right endpoint, so we're mixing the open parentheses on the left with the hard bracket on the right. Okay, cool. Well, what about over here? These are not compound inequalities. A compound inequality is what is the name for when you have sort of two inequalities in a row lined up like this. These are just a little bit simpler. This first one we know is describing all of the numbers bigger or equal to a. And graphically that's not hard to draw. A is a solution, and so are all of the numbers bigger than a. This is how I draw it. Well, how are you going to describe that using interval notation? That's interesting. I need to put the smaller number on the left and the larger number on the right, where these are the bounds of the interval. Now on the left, this is definitely bounded by a. But on the right, there is no boundary. So what number am I going to put here? It doesn't make sense to put any number on there. There is no right endpoint to this interval. So what I'm going to put there is actually infinity. That is a symbol that means to go on forever. And this interval does, in fact, go on forever to the right. Okay? Now the question is, what about brackets and parentheses? Well, the left endpoint a is included. So I do want to include a with a bracket. As we were saying, there is no right endpoint, so I'm certainly not including any right endpoint, which automatically kind of tells me I should use a parentheses. Also, a bracket really wouldn't make any sense. It would say that I'm including infinity in the set, but I'm not. And also, we saw that intervals that have right brackets and at the end of their interval notation have a largest number in that set. There is no largest number in this set. So also for that reason, it should have a parentheses. In fact, whenever an interval goes on forever in one direction or another, it always is going to have a parentheses. So whenever you see an endpoint, whether it's a positive infinity or a negative infinity, it'll always have an open parentheses. Okay? It'll either have one of these two symbols. It'll never have a bracket associated with an infinite endpoint. If we looked at this inequality right here, it's very similar. It's almost the same, but we want to remove that endpoint a. So we've removed it, and now we're going to the right. Now, this endpoint, this interval, doesn't have a largest element. It goes on forever to the right, and we're not including it as an endpoint because there's no largest element here. There's also no smallest number in this interval, so we're going to put an open parentheses here. That's following the same convention as over here. You probably knew that when I was removing that endpoint, I was going to replace this with an open parentheses, and that is what I do. And of course, these inequalities could be going the other way. We could be saying that x is less than or equal to a, so my interval could be heading in the negative direction, in which case I would say this is the interval from negative infinity to a. Notice that I'm putting I know there is no left endpoint, but I am putting the smaller number on the left and the larger number on the right, the way that I said that I always do. You can certainly describe in words this set, all of the numbers from a to negative infinity, but you can't write them in that order when you're using interval notation. Negative infinity is the smaller of those numbers. A is the larger. So they need to go in that order. And down here, it's almost the same thing, but of course a has been removed. So now we're looking at all of the numbers from negative infinity to a, and we're not going to include either endpoint. So this is interval notation. This is how it looks in all 8 possible cases. All right, so now that we understand interval notation, let's return to functions and this question of what is the domain of the given function. And this time, let's give our answer in interval notation. So I'm looking at a function f of x. F of x is 3x squared plus the square root of 1 minus 2x. OK, cool. Again, I could ask you, is this particular number in the domain? Is this other particular number in the domain? But if I think about this all at once, the x squared part is not going to be tricky. I mean, you tell me any number in the world, any real number at all, I can square it and multiply it by 3. This part is going to go off without a hitch. But the square root function, you can't take the square root of every number. You can only take the square root of non-negative numbers. And that's what I say here. This boils down to something quite simple, actually. If your function contains a square root expression, as mine does, the 3x squared is not a square root expression, but the square root of 1 minus 2x is. If your function contains an expression like that, then the thing underneath the square root sign that I'm calling a has to be non-negative, has to be greater than or equal to 0. So if you want to answer this question right away, you should be concerned about, what could go wrong in a function like this. And nothing can go wrong here. But like I said, when taking square roots, taking the square root of a negative number would cause a problem. So my attention goes to this square root sign, and I immediately know that the thing underneath the square root sign, in this case 1 minus 2x, has to be greater than or equal to 0. So to solve this inequality, I'm going to solve it just like an equation. I'm going to maybe add 2x to both sides. So I find out that 1 is greater than or equal to 2x, and if I divide both sides by 2, I find out that 1/2 is greater than or equal to x. And by the way, that's the exact same thing as saying x is less than or equal to 1/2. Okay? Again, the hungry fish is eating the larger number. And in both cases, the fish is eating the 1/2. So 1/2 is bigger than x is smaller than 1/2. These are saying the same thing. Okay? And how do you say it in interval notation? Well, maybe you want to use as a stepping stone the graph just to help us out. We see that x is less than or equal to 1/2. So if this is 1/2, I'm talking about all the numbers less than that or equal to that. That would look like this. And hopefully now it's clear that in interval notation, these are all the numbers from negative infinity to 1/2. You can't include negative infinity as an endpoint, but you do include 1/2 as an endpoint because x equals 1/2 is in the domain. Let's look at this one. This one says find the domain of this function. Well, we know what we're doing now. We're scanning this and seeing, does it have a square root expression? It does, right here. At some point, we have to take the square root of 3x minus 10, and that's an opportunity for this program to crash. It would crash if 3x minus 10 was a negative number, but we're going to insist that 3x minus 10 is at least 0. Okay? As long as x satisfies this inequality, it's in the domain. And so I'm going to solve this similarly. I'm going to add 10 to both sides. I'll find out that 3x is greater than or equal to 10. So x must be greater than or equal to 10/3. If you want to, you can still continue to draw the graph. Show me where 10/3 is. If x is equal to 10/3, that's OK. Or if x is greater than 10/3, that's OK. So in interval notation, I would write this as 10/3 is the left endpoint, included. Infinity is the right endpoint, not included, never included. That's the answer here. All right, so let's stick with this question of finding the domain of functions, but let's increase the level of difficulty just a little bit by looking at functions that have variables in their denominators. This will turn out to be a little bit trickier, and we're going to need a new rule. Now, the rule is not anything that you don't already know. The rule just says that if your function contains a fraction, something over something, I call it a over b, then the denominator b is not allowed to equal 0. b does not equal 0. Okay? Now, in this question, I say find the domain of f of x equals, and I have a fraction. The numerator is 5x plus 3. That's fine. You tell me any number at all, I'll multiply it by 5 and add 3 to it happily. Nothing can go wrong. But then you tell me to divide it by this, and since there's some user-generated input, x, involved, it's possible that x is a number that would cause this denominator to be 0, and the program would then crash if it ends up trying to divide by 0. So the rule is taking care of all of the work for me. If I see a denominator, and I do, I automatically know what to write down. I know that the denominator is not allowed to equal 0. X squared minus 16 does not equal 0. OK, so what does that tell you about the values of x that are allowed or not allowed? Well, specifically, this is going to tell me what x is not allowed to be. I don't think it's very hard to see that I'm going to factor this into x plus 4 times x minus 4, because that is a difference of squares. I know that that is not allowed to be 0. And I know that that means that x plus 4 is not 0. And x minus 4 is not allowed to be 0. Okay, and I'm writing not equal signs. If you wanted to change these to equal signs and solve for what values of x cause the denominator to be 0, and then just know that those are not in your domain, fine. I'm just writing it this way to remind myself that these are the number I'm solving to figure out, what do I know about x when I see this expression? I know that x is not allowed to be, Well, x is not allowed to be negative 4, and x is also not allowed to be 4. So this is what it's boiled down to. X can be any number at all except for these two numbers, plus and minus 4. Now, on a number line, I know how to graph that. Here's my number line. I'll maybe label it x. This is supposed to represent all of the possible values of x. Negative 4 and positive 4 are numbers of interest. And all of the numbers that aren't negative 4 and aren't 4 look like this. It's all the numbers below negative 4. It's all of the numbers bigger than positive 4. And it's all of the numbers in the middle. Now, what's interesting here is that by removing two numbers from the number line, we're left with 3 separate intervals. And if you want to describe this domain in interval notation, it's going to require 3 intervals in the answer. So for this interval on the left, I'm going to write negative infinity to negative 4, neither endpoint included. For the one in the middle, I'm going to write negative 4 to positive 4, neither endpoint included. And for this third interval on the right, these are all the numbers from 4 to infinity, endpoints not included. Okay? So this interval describes that one, this interval describes that one, and this describes that one. What do I want to do now? Well, the answer is I want to take their union. So I'm going to just insert a symbol in between these intervals. It is a capital U. That's what it is. And it's the symbol for union. Okay, the union, this symbol is read union, so it's this interval, union, this interval, union, that interval. A union joins intervals together to make one set or one domain. When you go to a wedding, they say, we are here to celebrate the union of these two people, where two become one. That's what we're doing here. We're taking two things and unioning them together, and then a third thing and unioning it together, so that while these are 3 separate intervals, they're also joined together to be just one thing that I'm calling the domain of this function. So this domain consists of 3 intervals, and its domain is the union of those intervals. So just know that sometimes we have to put a union symbol in between our intervals to join them together. And in particular, we do that every time you need to skip over a number. You're going to take all the numbers to the left of that number and union them with all of the numbers to the right of that number. It happens pretty regularly. In this example, I asked the same question, what is the domain of this function? Now, don't forget the rule from before. The rule from before says that when you have a square root expression, and I do, the thing you're taking the square root of, in this case 3x minus 9, cannot be 0. It has to be at least 0, 0 or bigger. Okay? And let's just stick with that for a second. So that means that 3x needs to be bigger than or equal to 9, and so x needs to be greater than or equal to 3. Okay, fine. I know something about what values of x are allowed and what values of x are not allowed, but there's something else to consider here because there is a denominator. And this new rule tells me that when there is a denominator, the denominator is not allowed to be 0. So seeing that there is a denominator of x minus 8, I know that x minus 8 is not allowed to be 0. Well, if I add 8 to both sides, that means that x does not equal 8. So this is what I know. X is bigger than or equal to 3, but also x is not 8. It might be helpful to visualize what that looks like on a number line. I can see that 3 and 8 are the numbers of interest. Now x is allowed to equal 3. And x is allowed to be bigger than 3. But x is not allowed to equal 8, so we must skip over 8. And when I have to skip over that is the end of this interval on the left and the beginning of this interval on the right. So the way to describe this in interval notation is to write 3 comma 8 with an open parentheses because we're not including 8 here. And then on the right side, I pick it back up with the interval from 8 to infinity, and I take the union of those two intervals. So this is how you describe this domain using interval notation. All right, and lastly, let's just look at 2 final examples. that will tie together all of the ideas that we've talked about so far, like in this first one. I say find the domain of this function f of x. Now, the rules that we've seen say that if you see a square root expression, and I do, I see the square root of 9 minus x, that the thing you're taking the square root of has to be greater than or equal to 0. So 9 minus x is greater than or equal to 0. This must be true. Also, if your function has a denominator, the denominator is not allowed to be 0. So I also know that the square root of 9 minus x is not equal to 0. These are the two conditions that I need to use to determine the domain. And the first one is pretty simple. If something does not equal 0, then after you square it, it still doesn't equal 0. Okay? So 9 minus x cannot equal 0. Well, now I know that 9 minus x is greater than or equal to 0, but actually 9 minus x is not equal to 0. So really, I suppose 9 minus x is just strictly bigger than 0. It's not allowed to be equal. It could be equal if x was, if x was 9, you would have 9 minus 9, and you could take the square root of 0, but later on you could not divide by 0. So for that reason, x is not allowed to equal 9. X has to be less than 9. These are saying the same thing, whether you say 9 is greater than x or x is less than 9. This is describing the domain. And in interval notation, I think that's a simple enough one. I can jump straight to saying, whoops, that the domain is all numbers from negative infinity to positive 9, and we will not include 9 in the interval. That's your domain. For this function g of x, what's going on here? Well, I've got a square root expression. It's the square root of 4 minus x, so I know that 4 minus x is greater than or equal to 0. The other thing that I know, looking at this function, is that it has a denominator, and its denominator is not allowed to equal 0. So I'm going to write that down. X to the 4th minus 5x cubed minus 6x squared is not equal to 0. Now I just have to whittle these down to the point where I can see what the domain is. This one's not very hard. If I add x to both sides, I see that 4 is greater than or equal to x, or in other words, x is less than or equal to 4. OK, so 4 is the largest number in the domain, for sure. What else do I know? Well, I know that this is not equal to 0. And to help me see what this is telling me about x, it might help to factor. I can pull out an x squared. I'd be left with x squared minus 5x minus 6. And I can factor a little bit further. I can factor this quadratic into, let's see, I think x minus 6 times x plus 1. And this tells me that x squared cannot be 0. X minus 6 cannot be 0. And x plus 1 cannot be 0. Notice that I'm making all of the moves that I would normally make if this was an equals sign instead of a not equals sign. All of the same rules apply. And so now I can tell you that, OK, x is not 0. X is not 6. And x is not negative 1. Now, I already knew that x was less than or equal to 4. So to tell me that x is not 6 is not anything new. This one right here is redundant. That'll happen sometimes. OK? But the other ones are telling me new information. If you look at a number line, what I know is that x is at most 4, but it's not equal to 0, and it's not equal to negative 1. So what numbers are you left with? All of the numbers from 4 and below, except for these two. So that actually leaves me with 1, 2, 3 intervals of numbers. What are those intervals? Well, the first one is everything from negative infinity to negative 1, right endpoint not included. Then we have all the numbers from negative 1 to 0. And lastly, we have all the numbers from 0 to 4. 4 is included. I'm going to take those 3 intervals and take their union. Now this is one set of numbers. That set is called the domain. This is the domain in interval notation.